Hello, my name is Steve Wallace, and I'm going to give a presentation on the effect of continuous suppression of heparan sulfate on arterial endothelial alignment and gene expression under several different shear stress waveforms. First of all, I'm going to start off the presentation about how we got motivated to do this project and really talk about some of the results in the literature. And past papers have found out that heparan sulfate acts as a mechanotransducer, and they were able to show that through using either bovine aortic endothelial cells or HUVECs. And what they did is they did a batch treatment of heparinase to remove about 50% of the heparan sulfate on the surface of the endothelial cells. And after this batch treatment, they then exposed the cells to flow. And what Tarbell's group found is that after 3 hours of flow, this heparinase treatment or removal of heparan sulfate totally inhibited the nitric oxide production. Another study by Forbes Dewey's group showed that after 24 hours of flow, that the cell alignment was totally inhibited. The shear-induced cell alignment was totally inhibited just by removing 50% of the heparan sulfate before you even expose the cells to flow. So this really motivated us to look further into what heparan sulfate is doing. So our goal was to further elucidate the role of heparan sulfate in mechanotransduction. And what we wanted to do was look at various shear waveforms that haven't been looked at before. We were going to do a 24-hour flow, and we also wanted to do a continuous heparinase treatment instead of the batch treatment that others have done in the past. Our endpoints for our study was going to be, again, cell alignment and NO production. We're also going to add look at some gene expression using a microarray. So for our different shear stress waveforms that we concentrate on throughout this experiment, we have what we call a non-reversing shear waveform, which is shown here in the blue. It's going to have a mean shear of 15 with oscillations of amplitude of 15. So it's 15 plus or minus 15, and everything is done at a 1 hertz frequency. The oscillatory waveform is shown here in the red. It has a mean shear stress of 0, and its amplitude is 15, so 0 plus or minus 15. And we have a static condition, as well as a steady 15 dynes per square centimeter condition. So this is done throughout all of our experiments. We did add a couple more shear waveforms, which is at 7.5 steady, and what we call a reversing waveform here at 7.5 plus or minus 15 for the first experiment on looking at how does the heparan sulfate expression, how is it altered due to the different shear stress waveforms. And these are the results that we got. That flow actually increases the porcine aortic endothelial cell heparan sulfate expression. So we normalized all of these heparan sulfate immunostaining to a static condition that was ran in parallel. We found that either oscillatory flow or steady flow at 7.5 or reversing at 7.5 and our steady at 15 and our non-reversing at 15 all show they're significantly upregulated compared to the static. So it didn't really matter which shear waveform we exposed the cells to, they all were significantly more than the static. Doing a one-way ANOVA across just the flow, the flow cells show that there's no real significant difference that we found between each of these waveforms. So it's really an indication to just flow along is causing an increase in the heparan sulfate. So that led us to think more about the batch treatment versus the continuous treatment, because we wanted to do a 24-hour flow, and we were worried if we did a batch treatment like others have done in the past, that the flow would then regenerate the heparan sulfate during the 24 hours, and we wouldn't have continuous inhibition of the heparan sulfate production. So what we did is we have pre-flow porcine aortic endothelial cells that have some heparan sulfate on them, and what I showed you is that the steady non-reversing oscillatory flow greatly upregulates the expression of the heparan sulfate on the endothelial cells. And what we decided to do is do a continuous heparinase treatment during the flow, having the heparinase within the media of the flow experiment, and so that we can have continuous suppression of the heparan sulfate. And so we were able to suppress, compared to the control flow, about a fourth or less of the heparan sulfate on the surface of endothelial cells. Here's some representative images of our The green is the heparin sulfate expression on the top of the endothelial cells. Pre-flow, post-flow, you can see that there's a lot more heparin sulfate. And when we had the heparinase treatment in there, there's very little, even probably less than the static control for heparin sulfate. So there's a continuous suppression throughout the 24 hours when we do add the heparinase in there. So that reaches our goal to be able to suppress the heparin sulfate. Here's the data that backs up what I was just explaining, showing that at 25% we suppress it about 25% of what it would be in the control flow, and even less for the non-reversing and the oscillatory.